efficiency, whatever. Yes, so the Željko Rapljenović is doing his PhD research in the program of the condensed matter physics area, and the title of his proposed research area is Hexagonal Ferrites, Hexagonal Ferrite equation. His supervisor is Tomislav Ibek from Institute of Physics also, and his co-supervisor is Aleš Omerzu here from University of RIJEKA Department of Physics. So, Željko, the stage is yours.
Thank you.
Please.
So, hello. My name is Željko Rapljenović, as Professor Kreister already said. Today I'll be talking to you about my research topic, the so-called hexagonal ferrites. These are the crystals which crystallize in the hexagonal crystal structure, and they are based on iron oxides. We can consider this class as a meta class because it contains many different types inside. So, for example, and these types have general formulas. So here is an M-type hexaferrite with the general formula A, iron 12, oxygen 19, where A is an earth alkali metal. So this is the simplest case of the hexagonal ferrites. And then, as we proceed down the line, these general formulas get more complicated. These materials are important for industry and science. And for example, here is the picture of the plastoferrites, where in the plastic matrix are embedded hexaferrite particles. So here is the structure. It is projected on the Ca-B plane. Here the yellow atoms represent oxygen atoms. Green atoms represent the usually earth alkali metals. And the small orange and red atoms are the iron atoms in different coordinations. So in this picture there are also some symmetry elements. They are lowly visible, but this is a mirror plane and this is an inversion center. So they're usually crystallized in the center symmetric structure. And this structure, so here are the 6 main types of hexaferrites. The so-called M, W, X, Y, Z, and U types. And we see that this structure gets complicated and grows in length in the C-crystallographic direction. They were discovered in 1925 in the mineral magnetoplumbite. In 1938, this crystal structure was deduced as being hexagonal. And since then, the research went on. They found their way in application. So, for example, a fun fact is that the 90% of total magnetic materials produced globally is hexaferrites, are hexaferrites. Someone calculated like it is 50 grams per person. Another application is in gigahertz electronics, where they have strong absorption due to the ferromagnetic resonance. From the scientific perspective, they're hosts to multiferroic and magnetoelectric phases. And here in this picture you can see this one hexaferrite. I don't know if it's visible, but the last layer has this beautiful hexagonal structure. So it does not just end on words. Here is the growth of yearly number of hexaferrite papers per year. So it ends in 2011 with, let's say, 200 papers, and in 2019 it has already doubled. So here is the example of this why the research is growing, why the interest in this material is growing, because of their potential magnetoelectric effect. So here is an example in Z-type hexaferrite with strontium, cobalt, iron, and oxygen. This material has many different magnetic phases with cooling, and one of these phases is this transverse conical phase, where the spins have this conical structure. And if we cool this material in electric field and we enter this phase, we find that it is a host to the magnetoelectric effect, because if we increase magnetic field, we see the change in polarization. Also, if we cool it in the opposite with electric field in the opposite direction, we get opposite change. which is explained via the change in the speed helicity of this structure, so it changes helicity. Yeah. One more example, they saw that the properties of these hexaferrites could be enhanced if it forms these fibrous structures. The properties of permittivity and permeability in the gigahertz range. So here, this is a rather novel thing in hexaferrites. So we saw an example of magnetoelectric effect, but this is somewhat an exotic phase. But usually in the room temperature there are ferrimagnets. So here is the picture of M-type hexaferrite with his ferrimagnetic structure, where all of these colored spheres, not the gray one, are different coordinations of iron, and the arrows represent the magnetic moment at the site. And we see that some of these moments point up, some point down, but the general consensus is pointing up, and this is a ferrimagnet. They have highly anisotropic properties in structure, and the electric also properties. From the perspective of magnetic anisotropy, they are uniaxial. They have a uniaxial anisotropy, and they are insulators which are very sensitive to synthesis. As we saw, the structure is complicated, but it can be simplified if we view it as a sandwich-like structure which is formed by different layer building blocks. So here is the S, R star, and S star layers, where the R star and the R layer are the same layer, but it's rotated by 180 degrees. And on this table is the summarized of their the main types of hexaferrites and their building blocks. So, for example, we saw this M-type has this SR, S star, R star composition, while the Y-type has 3 times repeating ST, ST, ST. So these layers, we can see them here. This is the S layer, the so-called spinel layer, which comes from the cubic form of iron. Here are the R and T hexagonal layers. And what is special, there is a special coordination of iron in this R layer, which is this coordination is called the so-called trigonal bipyramidal coordination. Here it is zoomed in. Iron is located in between 5 oxygens, which form this two-sided pyramid. Yeah. And so this is just a quick recap of hexaferrites. They have a large unit cell, as we saw. They form sandwich-like structures, and the understanding of the structure is crucial. I didn't say it, but this trigonal bipyramidal site, which I showed here, is held accountable as being the responsible party for many of the hexaferrite properties. Here also is the table, I didn't explain, different hexaferrites and the length of their C-axis, which can grow to about 8 nanometers. So, my research is mainly focused on the M-type hexaferrite. Here it is his crystal structure. It has a general formula, AB12019. We saw it before, but here I want to emphasize that we can substitute iron atoms by another ion. The parent material is the barium hexaferrite, the so-called BAM, here, with his formula. They crystallize in the point group 6/mm, with this is 6-fold rotation and 3 mirror planes for every unique axis. And they are uniaxial ferrimagnets with high Curie or Néel temperature, about 400 degrees Celsius. From crystallographic point of view, they have 5 crystallographic different iron sites with 3 coordinations, where one, this bipyramidal iron site here, is color blue, and other than that we have octahedral and tetrahedral sites. So I have selected a few topics about hexaferrites that I want to present to you. These are the so-called dynamical disorder, the question of the bilateral like response, and the incipient ferroelectricity and anti-ferroelectricity and frustration. So here it is again, the pyramidal iron site. There is a question whether the iron atom resides in this equatorial plane formed by these three oxygens, or whether it is off-centered to one of the apical oxygen atoms. This question is important because if it is located in this equatorial plane, then the structure is centrosymmetric and no permanent dipoles can exist. But if it is off-centered to one of the oxygens, then the structure is not centrosymmetric, it is polar, and we can have permanent dipoles forming. So different experiments point to different things. For example, neutron diffraction at room temperature says that the structure is polar, so the iron atoms are located in this distorted tetrahedral positions. While upon cooling, they stabilize in this equatorial plane and thus form a centrosymmetric structure. Other experiments there are experiments with terahertz spectroscopy and Raman scattering, which show some phonon softening, which is attributed to behavior that at room temperature they are dynamically distorted between these two tetrahedral positions, and upon cooling, they can stabilize either in the tetrahedral positions or in the bipyramidal site. And here is the free energy diagram of this proposed behavior. So we saw it with this conundrum about the dynamical disorder would have influence on the dipolar response. So there was some paper that proposed this relaxer behavior. So a relaxer can be understood easily from the ferroelectric phenomenology. Here are the three types of ferroelectrics. So here is the electric function versus temperature, and every line here corresponds to different frequency. If you have a displacive ferroelectric, which goes from high symmetry structure to the low symmetry structure, there exists there. On the transition, there is a structural phase transition where the dipoles are created and immediately ordered, while in the order disorder we have already permanent dipoles existing in the high temperature range, and in the low temperature range they order to ferroelectric state. And we see the difference between these two curves is the dispersion of the dielectric peak. And for the relaxer ferroelectric, we have the large dispersion, and in both the amplitude and the position of the peak. This is explained by the forming of a glass-like state, which has polar nanoregions forming, which are distorted. They have large disorder, and it shows this diffuse behavior. So for the relaxer we saw now the example of a relaxer in the ferroelectric subsystem, and there for the birelaxer we need two relaxers, and the other would be in the magnetic part. So we did some measurements have been performed by our collaboration of our group with a group in Russia. So here are the dielectric measurements, dielectric function versus temperature, where every line corresponds to different frequency. And we see similar behavior to relaxer behavior. And if we take a spectrum at every temperature, we get this dielectric function versus frequency, which shows high dispersion of the dielectric function, and which follows a Debye-like process. What we also found that the similar thing happens in the ferrimagnetic subsystem. This feature, which is similar to this feature but exists, and we extracted using the Cole model relaxation times that govern this process. This is the Cole model. Here is the relaxation time. And in this Arrhenius plot, we see that this relaxation time follow activated behavior. So this means that there is similar process governing both these two relaxations. This could mean. Other people have also measured the electric response on the parent compound. The compound before had barium in some percentage substituted for lead. They measured, this is inverse, the electric susceptibility versus temperature. And here in this region, it follows the Curie law. And on the low temperature, there is a deviation from the Curie law, which they interpret as onset of ferroelectricity, the so-called incipient ferroelectric phase, which incipient means upcoming, so not developed. And other groups have also done these measurements, so have done similar measurements and got similar results. So for example, here's they explain it a different way. Here's the crystal structure, here is the outer layer where the trigonal bipyramidal sites reside. We see that they form a triangular structure, and if they are allowed this off-centering, they are subject to frustration. So frustration is if we have one dipole moment pointing in one direction. And I also propose that these dipoles are antiferroelectrically coupled. And okay, so if we have a dipole at this site in this direction, the next neighbor should be in the opposite direction. But for the third neighbor, we don't know. It has both positions available. It does not have a unique direction. And they have proposed also that this material could be the host of exotic phase, the so-called quantum electric dipole liquid, which would have similar phenomenology to the quantum spin liquid. So my thesis will be we will research. I will research in my thesis magnetic and electronic properties of variously substituted hexaferrites. We have different single crystals of different substitution of barium and lead, and we have an option to change iron with either aluminum or titanium. The substitution of aluminum has been calculated using DFT that it would have the largest influence on the structure and thus possibly stabilize the ferroelectric state. Here is the graph of a difference in between the paraelectric and the ferroelectric state versus the ionic radius of the substituted ion. We also will research some nonlinear magnetic and dielectric effects, magnetic anisotropy, and possibly local structure. So here is a sneak peek to some of my results. They have been measured on some of our results. They have been measured on AC susceptimeter. So AC susceptibility is the AC susceptibility measurements give us a complex susceptibility. So here rows represent real and imaginary parts of susceptibility, and we have this feature I showed you earlier in the Beer-Laxer-like response. And we see here's this, and we introduce in this structure a percentage of aluminum. So we not a percentage, but we let's say substitute one iron by one aluminum and by 3.3 aluminum. And we see that this feature, which we attributed to some relaxer-like behavior, is moving to high temperatures. But after we introduce 3.3 aluminum, this feature is gone and it is replaced by this feature which looks like a super paramagnetic transition. This could mean that we lost the long-range order in the structure and the particles that resist are single domain. And for every this process, we can extract activation energy that governs it. We were able to correlate it with transport measurements. So here is the resistivity function of inverse temperature. Here is the temperature scale for reference. And we see that activation energies so we can fit these resistivity curves to the activated behavior, and we see that this activation of resistivity and the AC susceptibility follow similar behavior upon substitution. We interpret this as they're somehow in some way correlated. Future measurements will be also done. We will try to see if there is any magnetoelectric effect. We've done some measurements, but they're, let's say, inconclusive. And this is it. I want to thank all the people that work in all of these laboratories at Institute of Physics, and these two projects for funding my research. Thank you. Do you have any questions?
Okay, thank you, Željko. Now we are passing to this second part of the defense, which is questions. First from the members of the council, please. Silvia,
You can expect.
Silvia Tomic, then
Okay.
Rapljenović.
Maybe let's start from the. I remember that you said something like you explained this importance of this pyramidal unit for ferroelectricity for polarization.
Yeah.
And you said that there is this oscillation of this iron side. Okay, this explains dipole moment, which is nicely in this second picture shown. But then one moment you said that on cooling, that these oscillations disappear or change or something. Can you say more about that?
I'm not sure which part, but about, okay. I think you're talking about, about Newton diffraction or about the dynamical disorder. So Newton diffraction says that...
without dynamical disorder.
Okay.
Which is also seen from X-ray and Mossbauer, whatever.
Okay.
There would be no explanation for ferroelectricity in the parent compound.
Ferroelectricity?
Polarization.
Polarization.
Okay, you just plotted 1 over epsilon according to Rowley story, but can you make a plot of epsilon versus temperature linear scale?
Yeah.
Wow.
So something like this.
Yeah. Okay. So this is the electric constant follows so-called Barrett behavior, which actually means that there are polarization down to extremely low temperatures. But okay, so said there is deviation of Kirillov. There is no ferroelectric ground order because due to quantum fluctuations.
Yeah.
Okay, which make this epsilon, which is on the y scale, maybe yes for people just to go like this. Okay. If I think about this experimental result, then I would never say, and if this pyramidal unit is responsible for polarization, that this dynamical disorder ceases or freezes at below some temperature.
Yeah.
Then I do not understand how it is measurable down to low temperature. So what is is it still open?
Yeah, the structure is still open. There is no consensus about it. So
some people say that this freezes, and some.
Yeah.
What is the experimental signature of freezing of this dynamical disorder?
Some phonon softening, anomalous phonon softening. This is
Okay.
okay. So the interpretation for this Newton diffraction, they say also that it freezes and that on the average this is non-polar structure because it's antiferroelectrically bound. But well, it's a question. I don't know how to say about it.
But okay, regarding this, can you show again this aluminum, your aluminum results?
Mm-hmm.
Okay, but I would just maybe you can comment what happens. Okay, we start from parent compound.
So this is our parent compound. We do not have access. We do not have access to the. This is the barium substituted with lead. We have. This is more of a lead. Yeah.
But if you take this barium iron oxide with this behavior, Barrett-like, okay, the electric constant, other people measured.
Yeah. Okay.
Okay. By the way, what is really important experimental evidence for this? That this is for this unit, that oscillations of iron is along c-axis. The electric constant is measured along c-axis and in AB. And there is nothing,
it shows different behavior.
This is really very important.
Yeah. Okay. So the Kirillov would say.
To me, this is the key evidence.
Okay.
Okay. Have you something against?
No.
I'm just asking.
I have how to say intrinsic skepticism of this.
You think that
they didn't show no frequency measurements. Okay. I believe this graph. Okay. This is the same, similar as Rowley.
And now, so just coming to this, so what I wonder, how this Barrett-like behavior in the parent compound get transformed into relaxer behavior measured in Zagreb. To me, this is the principal question. What is changed? And now, when I search the literature, if you look, you take parent compound with barium and look at the doping with strontium. Do you know what happens when you dope with strontium?
Yeah, dope it or just the strontium?
The
pure strontium.
No. Okay, and you come finally to the pure, but
this moves to higher temperatures for the strontium sample, as I know.
So what happens? I mean, regarding these oscillations of iron, they become smaller and smaller.
Okay.
So, but still, this behavior remains, but this is pushed to lower temperatures. So strontium, nothing really does. It doesn't produce relaxer. This is what I want to come to.
Okay, but this one also, by their reasoning, does not produce a relaxer.
But I'm just, if you dope, you want to understand what produces disorder. So how come? My question is, how come that strontium doesn't produce disorder to get transformed this Barrett behavior into relaxer, and if you put lead or you put aluminum, you have already a relaxer. So to me, it would be interesting to understand why this transformation of the electric response, what is the cause of it? You see what I mean? Can you get it with your aluminum thing? What is the final result?
This one?
Yeah.
So this is a super paramagnetic behavior.
Super?
Super paramagnetic.
These are magnetic.
This is magnetic measurements, not the electric.
Okay. And the electric?
Let's say I'm skeptical about them. I have measured with different contacts and I got different results, so I'm not able to distinguish whether it is something intrinsic or extrinsic.
No, I just wonder if these people, I'm pretty sure that these people understood how to make contacts, which is the biggest problem in the electric response. These Shen people.
Okay.
This physical UB is excellent paper to me.
Yeah, I know.
So maybe it would be good to come in contact with these guys, and maybe there is a secret. In the electric response is always problem. You have to put these contacts, and then these influences you never really know. You can't distinguish directly with whether the measurement is correct or not. You have to always make different tests, etc. Yeah. Okay. I will stop now. Maybe I will have questions later, but.
Zdravko.
Well, I'm not well much involved in this type of structure, but I just wonder what's happened about TC.
What happens about
Yes, how this thing changed about TC? What is going on?
there is a phase transition to
Yeah.
to
What kind of what
second order phase transition to paramagnetic state, probably. Yeah, I didn't see no high temperature measurements, but yeah. Wait, maybe just a second. I have some graphs.
because it's so complicated structure, so it would be nice to see what's going on
higher temperatures.
above.
Above TC, the
Yes.
ferromagnetic TC.
Yes.
Ferromagnetic. I know now from my head. I remember some paper, but they made high temperature measurements of Raman, and they found there was some result that, but from this high temperature measure, they say that high temperature again is not so interesting, but something happens at lower temperatures. There's some kind of local magnetic transition. So for the high temperature, I don't know. Yeah. So, I mean, I have
But
measurements.
if you cool the system when you above and then you cool the system, can you get again this structure? Or not?
If I pull,
If you cool. Yeah.
What? I'm sure. I understand.
What would happen?
With cooling,
Yes.
from the magnetic or the
Yes, for the moment.
magnetic, it just behaves. I have a picture just here. This is thrown out of the presentation, but here is an anisotropy constant versus temperature. But the anisotropy is proportional here in the system for, and also this is polycrystalline material. But it follows this, let's say, normal behavior for ferromagnets.
Okay. Thank you.
Okay, so first, what kind of samples you've got? Are there monocrystals?
There are single crystals.
Single crystals.
Yeah.
Okay.
So I didn't mention this, but in few attempts at this, I should said that the polycrystalline. Usually this research is done on polycrystalline, but lately there have been an onset of single crystals.
Okay. So you mentioned that you will measure also electronic properties. What specifically you refer to? What kind of electronic transport?
Transport. Transport and polarization measurement. So we will try to search for this ferroelectric.
But you didn't mention actually what the electronic structure of these materials. What kind of electronic structure you got? What are these materials?
So they are semiconductors.
What kind of gap they?
It's a very small gap. So
Very small gap.
yeah, I didn't mention it, but here it is. So here is the activation energy. So times 2 is the gap. Yeah, probably yeah. So it's about 1000 Kelvin, which is 0.1 electron volt. I can.
Okay.
Yeah, so something really small.
Okay. I just wanted to also to ask you. I mean, whenever you have a semiconductor, actually you have on your surface band bending. Or possibly also Schottky barrier formation.
Yeah.
So I just wonder, are you taking into account this effect when
For transfer measurements? Yeah. Yeah.
Transfer properties?
Yeah. Yeah.
Because I guess, I mean, on the surface, because of some defects or anything, you will form some states which will accumulate charge and then change your surface structure with respect to bulk. So I don't know how this may affect measurements, but that's
I saw some feature that looks like a Schottky barrier.
And also, is there any change of the electronic structure with temperature?
So the gap changes, but it changes.
So there are no kind of phases or
There is no phase transition.
No
so
phase transitions in electronic structure. Okay. And I mean, of course, I'm interested. are there some good photoemission measurements on these crystals regarding the band structure? If you are aware?
Not that I would.
I mean, you are going to Soleil.
No.
That's the place where one can get hold on the very nice machines. Like, for example, nano ARPRES.
But I will, if I'm going, but I will not be measuring
I
by
know,
the.
I know.
I will measure.
I
it.
just wonder. I mean, is there any?
I didn't see any. So,
Okay.
any more questions?
No, thank you for the moment.
Could you go to slide number 12 again? What is EPA here?
Order parameter.
Order parameter is probably connected to this relative separation to the center.
Yeah.
Okay, and F is free energy.
Yeah.
So how would you describe this graph to, let me consider an idiot? Try to explain.
So on high temperature there is just one minimum, and after we reach a critical temperature, the TC, then 3 minimums exist. So bifurcation starts to happen, and upon further reducing temperature, we have just 2 minima, and here, no, what can I also say? This is the first order crystallization.
Order transition.
No, this would be first order.
First.
Yeah. But somewhat first order. For the first order, it would be this minima should be the maximum. This central minimum.
Celia.
Look, to me, it would be much clearer to approach the problem again from the parent compound, barium,
Of course.
iron, oxygen.
Yeah.
Where there is a clear magnetic transition at 700 whatever, and there is a clear polarization behavior. Where there are DFT calculations, etc. More or less, everything is clear there. And now to see what doping or exchanging iron or barium with some other ion does.
Yeah.
Like strontium, for instance, which just makes these shifts smaller. And now when you put lead, puff, everything is changed. So it looks like it makes really big disorder in homogeneous environment there.
Yeah.
From where relaxer comes. Before there is no trace of relaxer.
Yeah, it could
So-
come from the substitution, but
So why doesn't come with substitution of
partial.
strontium?
of course, okay.
This is the question. Yeah,
Maybe.
why? You must. I mean, So it would be much better to. It's easier than to follow the line what happens in the systems.
Can I just say?
I would ask Boris to produce.
We asked. We
and-
asked for the parent compound, but they don't have any. I think they said something like they don't have anything for radio
And,
frequency.
yeah,
so
and why they
this
couldn't,
is
or they had
lost.
their reason why they made immediately lead substitution so high, 0.7. Why they didn't start from 0.2, 3, and then
If I may, maybe.
Yeah, but,
So as far as I understand, it wasn't possible to create single crystals, large single crystals. They just couldn't.
they couldn't produce.
They couldn't produce
Okay,
samples.
okay,
That's
this
it.
is a good reason.
It is unfortunately a good reason. Yeah.
I mean, these guys have the Rowley and the one.
Okay, it's something you didn't mention, but I am interested if you wrote in your application that you are going to look at non-linear transport, domain walls, blah blah. So what do you expect to get from non-linear effects? What kind of non-linear effects you expect? What they could explain, tell? What is the difference between, so to say, linear motion of domain walls and non-linear? Well,
So,
just general. And why you then expect to tell something in these systems?
so I'm not sure what I said in the application, but from the nonlinear perspective, I was thinking about the to measure all how to say harmonics of the dielectric function. And I was the main goal for me is to maybe find ferroelectricity and probably to explain those results I have. And what do I expect with nonlinear transport with different samples? So, like I said, I want to not find a ferroelectricity because the paper here, this paper showed that the aluminum could stabilize the ferroelectricity, and we have a better composition
Aluminum
of
stabilizes ferroelectricity?
yeah.
Really?
Yeah.
There is a ferroelectric transition?
There could be, I'm sorry, could stabilize. Then this is the proposition. So they calculated this with DFT. They said, okay, if iron is substituted by aluminum, how would it change the phonon dispersions? And they found that the aluminum had the greatest effect, and so this is because. And they explained it because it's a small atom, it would have a larger tendency to go in this tetrahedral site and thus distort the structure. This is all I can tell.
So what about nonlinear effects? What are you going to measure? What you would like to measure? What kind of nonlinearity?
So nonlinear in polarization versus electric field. So the general polarization curves and
polarization in electric field. I'm just asking.
So
Maybe AC susceptibility in magnetic field. I don't know.
no,
Or electric field.
no, some how to say combined measurements of with electric field and magnetic field. So let's say the electric constant dependence of magnetic field and I don't know in general.
But regarding domain walls or domains, there are possibilities maybe even at institute to try to visualize, to see if there is, could you imagine apply some technique to visualize if there are really domains there, or this is just imagination?
At the institute, there are domains.
The second harmonic generation, Damir Dominko doesn't do such a thing. But interferometry, not really just measurement.
I'm not sure if he does it, but if he does, nice.
That would be
I will ask him.
idea to maybe just to look at.
I think I could also, in the laboratory of AFM, there is a possibility, is there? If I remember correctly, just to visualize ferroelectric domains, yeah?
In principle, I think.
Yeah, okay, in principle.
Which, what?
In the AFM, so it would be piezo response, something like that.
Something.
Like,
A big one for piezo response.
Maybe any trial to see if there is possibility to visualize domains that will be nice. Not necessary, of course, that nice addition to the thesis.
I agree.
Other questions from members of council? Sorry, Antonio, you are not member of council, but anyway. But there are no questions. There are no other questions. So please, supervisors and general public, Aleš, you.
Usually, when you have an ion in octahedral environment, you expect Young-Taylor effect.
Yes.
What's about Young-Taylor effect in these materials?
What?
What's about the Young-Taylor effect? Doesn't happen, or why it doesn't happen? Usually in such a structure, you will expect that you will have a Young-Taylor distortion.
Well, I'm not sure about the tetrahedral site, the octahedral sites for the Young-Taylor effect. Maybe I could see it from the structure, but does it seem distorted, this octahedral? But somewhat, yes, yeah. It seems distorted, but...
Usually then you break symmetry when the distortion.
Yeah.
So the ion will go from the central symmetry
the oxygen
position in some left or right. Okay, this is just, I was curious about this. Nobody is telling nothing about Young-Taylor in this material.
Not that I know of.
Yeah, there is a paper on that.
Yeah? Oh, sorry.
By Boris and others. Titanium doping, the Young-Taylor effects.
The titanium doping. Okay.
Okay. Another question is about this call model that you have. Here, this formula is a phenomenological one with this parameter alpha. Then you model with alpha what?
This is a broadening of relaxation times.
Of the distribution of the relaxation time. And in your case, what is this number?
Close to 1, so 0.9.
So big. So
no, 1 minus alpha. I always so 1 minus
you
alpha.
have 0.89 or something.
The alpha is then 0.1. But
Can you estimate the distribution? What is the broad? Is it the broad? How much? 100%? Or can you estimate from this number? So there are some so-called derivation of this formula with some integrals, and then you have a distribution function, and from the width of this distribution function, you get this alpha in principle. So you can estimate. You cannot, of course, you cannot exactly calculate, but you can estimate what is the broadening. You don't know. So it's less than point size in this graph. You see that on the y-axis you have relaxation time, this tau naught, and each of these points they have some distribution.
yeah,
Okay, maybe they're sharp. As you said, the alpha is small.
Alpha is 0.9.
Yeah. Okay, okay, then.
Antonio, you have a question.
Yeah, so a bit more lightweight question, I hope. So, are you thinking of making? In fact, I know that you were thinking of making MFM measurements, or magnetic AFM measurements. What I was wondering is, what would you expect to get out of that?
I expect to get the size of domain walls. Probably
on the surface.
On the surface, yeah. This is all we can get. For this aluminum sample, which is here, I would like to know what is can we see this, this single domain particles? Because we can then correlate it with this number. It is connected via some formula, but this from the activation energy of the AC susceptibility. So I extract activation energy from here, and it is connected to this volume. Thank you.
Just to follow up on this question, I mean, semiconductors are known to reconstruct on the surface.
Okay.
So, do you have any idea about the surface structure with respect to bulk structure?
We have some measurement, and it seems that the surface structure is is not, how to say, does not influence the.
It's not different very much, or is it?
What can all I can say is that from preliminary measurements on RICS, we found that there is no large difference between there is not large contribution from the surface, so it's not, probably then that means that it does not differ so much.
But you are going to make atomic force, magnetic force microscopy. I mean, it's only related to surface, not to the bulk structure.
Yeah,
so,
okay.
I mean, so what I'm asking you is, are you sure that your surface structure...
No, I'm not sure, but this is, let's say...
and how that these measurements will be relevant to understanding bulk structure, properties?
If we find something useful, of course, okay. If we
No,
find
I'm
something
just
useful...
saying, I mean, whenever your technique is surface sensitive, then you have to take care, I mean, about conclusions, because surface can affect your measurements very, very much. Yeah. Okay.
Yeah.
Just look at the silicon surface. It's a well-known and a Nobel Prize won on displaying STM on 7x7 reconstruction. I mean, it's a huge unit cell, so the semiconductors are known to make very, very strong reconstructions on the surface. Okay.
Any more questions?
Other questions?
Short technical question here on this slide. What was the reason that you changed the amplitude of the AC field?
Nonlinear effect. So we saw that the scale susceptibility, if we for this last sample, we had large difference between the low field measurements and high field measurements. So I made a whole sweep, so not sweep, but let's say 5 different measurements on few different amplitudes, and this is the one that gets, how to say, the activation energy saturates. Maybe this is a bad way to pronounce it, but if I measure activation energy depending on the field, I get some crazy large numbers, which upon reducing amplitude have some desaturation.
Okay, then you get the linear. So,
Yeah.
Even the 0.1 Ersted it's a very small. I usually use much higher field.
Yeah.
But this is interesting.
It is very, very small.
Yeah,
Very small.
Yeah. For this last one especially. So.
You look at it and it's non-linear.
Yeah. And here I didn't say that the Earth magnetic field has been compensated for. So we
one question more about this. Have you measured the nonlinear susceptibility? So higher harmonics, 2
Yeah.
omega, 3 omega, and so on.
Yeah, but on just for this sample and on higher amplitudes here. For this amplitude, no, but for the amplitude of 0.2 S that I measured, and I reconstructed the linear parts from the harmonics.
I'm asking because you know that you said this is super paramagnetic.
It looks like it.
So usually it's quite difficult to differentiate between super paramagnetic and spin glass behavior in AC susceptibility. But if you measure higher harmonics, then you will see the clear difference. If you have a spin glass, you will have all harmonics. But in a super paramagnetic, you will get only odd harmonics, first, third, fifth, and so on. And this is quite straightforward to see what you check.
But we measure always only odd harmonics.
Because look, this what you have a real part of magnetic susceptibility.
Mm-hmm.
In this behavior, this you also can get from the spin glass. Exactly the same. I know. But the difference is when this peak will disappear if you measure the 2 omega. So in 222 hertz.
Yeah.
I think.
I know what you're saying. So
with the locking, it's
It's yeah, okay, it's easy.
Easy to do.
Yeah, I measured harmonics up to 6 harmonic, something like that, but we do not measure the second harmonic. We only measure the third, 5th, 7th, because this gives us the linear.
Yeah.
Of course. Yeah.
Maybe just it's not
Okay.
to try to second and fourth. And
Okay.
we'll see. I have a small paper from 90s, from 98, on TD-86. I have oriental spin glass behavior, and first thermoelectric transition, and then the spin glass transition low temperature, and I was just playing with these higher harmonics. So in the thermoelectric you have all, and after this spin glass you can see that there is a difference in symmetry.
It's worth trying.
Yeah, okay, also. Have a book chapter with children progress and one on this side.
Hvala. Neko pitanje imamo vremena za jedno pitanje još za kraj. One question. Okay, if there are no more questions, I would like to thank Željko. Questions? Možeš pričekati samo malo dani. Ja bih zamolio članove vijeća da istoriju. Mogli smo imali samo jednu da postoji. Da, hvala da zamolio bih da te prvi četvr da napišu.